When you walk through the Viking Ship Museum in Oslo, the first thing that hits you isn't history, it's a contradiction. Because standing in front of you is a ship built around 820 AD, more than 1200 years old, not a replica, not a reconstruction, but the real thing, a vessel made of oak whose wood is still intact, where you can trace the axe marks left by the builder, where every curve shows the decision of a human hand. And this ship didn't just sit in a calm river, it crossed open seas, endured saltwater, storms, ice, and constant stress, and yet it still stands here today, solid and silent. And then you step outside that museum and think about something completely ordinary. A fiberglass boat, built in the 1980s, barely 40 years old, whose hull is already blistered, soft when you press it, with water trapped inside its structure, damage that remains invisible until it suddenly becomes catastrophic. And once that process begins, it never truly stops. And that raises an uncomfortable question. How can a wooden ship built without electricity, without chemistry labs, without modern science survive for over a millennium, while a so-called maintenance-free modern boat begins to fail within a few decades? And the answer isn't luck, and it isn't burial conditions. It's a collision between two completely different ways of understanding materials, because the Vikings did not see wood as a dead substance. They saw it as a living system. They didn't simply cut down trees and force them into shape. They studied them, observing growth rings, grain direction, and natural curves, choosing parts of the tree that already bent the way a ship needed to bend. So the wood fibers were followed rather than cut, whereas modern sawmills slice straight planks that sever fibers and create hidden stress points. And in Viking ships, stress was distributed across the structure instead of being concentrated in weak areas. And then there is our modern assumption that water is the enemy of wood, something the Vikings never believed, because they didn't try to dry wood into stiffness. They sealed it with tar, animal fats, and natural oils that soaked deep into the material, rather than forming a brittle surface layer, allowing the wood to breathe, expand, and contract without cracking. While modern fiberglass is a rigid sandwich of plastic and glass fibers that traps water once it enters through microscopic cracks, a process known as osmosis, where pressure builds inside the hull, forming blisters and slowly weakening the structure with no obvious warning signs. And another crucial difference lies in flexibility, because Viking ships were not rigid machines but flexible bodies that moved with the waves, bending during storms instead of resisting them, much like a reed that survives by swaying while a solid block shatters. Whereas modern engineering often equates rigidity with strength, the Vikings understood that adaptability was strength, which is why their ships absorbed force instead of fracturing under it. And then there is maintenance, a concept modern culture tries to eliminate entirely with the promise of convenience. While the Vikings never believed anything valuable could be maintenance-free, their ships were treated like living things, regularly oiled, inspected, repaired, plank by plank, without destroying the whole structure. While modern boats are rely designed to be truly repaired, only replaced, and this difference extends far beyond ships, because it reflects how our entire civilization treats materials. We exploit them rather than cooperate with them. We optimize for short profit cycles rather than long lifespans. A boat that lasts 40 years is perfect for business. A boat that lasts 1,000 years is a disaster for industry. And that ancient ship in the museum stands as a quiet warning, reminding us that we are not necessarily more advanced than the past, only more impatient, not smarter, only more disconnected from the materials we depend on. And when you stand beside that Viking ship and place your hand on its oak planks, you realize that real knowledge doesn't always come from laboratories and machines. Sometimes it comes from an axe, a tree, and centuries of hard-earned experience. After World War II, a new miracle material flooded civilian life: fiberglass, a substance born in laboratories and perfected in war, used in aircraft fuselages, radar domes, submarines, and classified military hardware, where speed of production mattered more than longevity. And when the war ended, manufacturers were left with factories, patents, and a powerful new material, but no enemy to sell it against. So they went looking for civilian markets. And boats were the perfect target, because boats had always been expensive, slow to build, and dependent on skilled craftsmen. While fiberglass could be sprayed, layered, and molded by semi-trained labor in a fraction of the time, it didn't visibly rot like wood, it didn't rust like steel, and it promised freedom from centuries of maritime anxiety. And the marketing that followed were ruthless and confident. declaring fiberglass hulls to be indestructible, eternal, maintenance-free, the end of traditional boat building forever. And for a while the promise seemed true. Early fiberglass boats looked clean and modern. They didn't leak, they didn't creak, they didn't demand constant care. And compared to wood, they felt like a technological leap forward. But fiberglass doesn't fail the way wood or metal fails. It doesn't crack loudly, it doesn't snap suddenly. It fails quietly, invisibly, patiently. Because water does not simply bounce off resin forever. Even the hardest-looking fiberglass hull is not a solid wall, but a complex chemical matrix. And on a molecular level, water slowly migrates through it, moving between polymer chains, slipping through microscopic pathways that are invisible to the naked eye. And this process takes years, sometimes decades, which is why the illusion lasts so long, because by the time moisture reaches the interior of the hull, it has already passed the point of no return, finding tiny voids left behind during manufacturing, air bubbles, imperfect bonds, areas where resin never fully cured, microscopic pockets hidden deep inside the laminate, and inside those sealed pockets chemistry begins to turn hostile. Water reacts with leftover compounds from the resin, breaking them down, forming acidic solutions, and as these reactions continue, pressure begins to build, osmotic pressure that pushes outward from inside the hull, and slowly, silently, the surface begins to blister. Not from impact, not from stress, but from internal decay, and what looks like a cosmetic flaw, a small bubble under the paint, is actually a symptom of structure, raw breakdown. Because the laminate is being chemically dismantled from the inside out, the very material that was sold as eternal is being attacked by the element it floats on. And once this process begins, there is no true cure, only expensive delays, grinding away layers, drying the hull, reapplying resin, hoping the chemistry slows down enough to buy a few more years. But the pathways remain, the moisture memory remains, and the clock never truly resets, which is why fiberglass boats rarely die dramatically. They simply become softer, heavier, weaker, more fragile year by year. And the cruel irony is that the industry never lied outright. Fiberglass doesn't rot like wood, but it degrades in a different way, a way that is harder to see and harder to explain, and that is what made the promise of maintenance-free so powerful and so misleading. Because what was really being sold was maintenance blindness, a material that hides its damage until it becomes unavoidable. And this mindset spread far beyond boats, shaping how modern engineering thinks about materials, favoring sealed systems over living ones, convenience over inspection, replacement over repair, speed over understanding. And the tragedy is that older technologies were not inferior. They were simply honest. Wood showed its wear, metal revealed its corrosion. They warned you when something was wrong. Fiberglass stays silent, smooth and convincing while it fails. And this silence changed behavior. Owners stopped inspecting, stopped maintaining, stopped interacting with their vessels as living structures, trusting instead in chemistry and marketing slogans. And by the time the damage appears, it is already embedded deep within the hull, expensive, demoralizing, and often not worth fixing, which quietly feeds the replacement economy, where boats are discarded not because they are unusable, but because they are uneconomical to save. And this cycle reveals the deeper truth behind the post-war fiberglass revolution, that it was never designed for centuries. It was designed for speed, scale, and profit, born from wartime urgency and adapted to peacetime consumption. And when placed next to ancient vessels that survived through flexibility, repairability, and intimate knowledge of materials, the modern miracle begins to look fragile, not because it is weak, but because it was never meant to last forever, only long enough to be sold. And the unsettling realization is that fiberglass did exactly what it was engineered to do. It made boats faster to produce, cheaper to sell, easier to market, and quietly disposable. And the real failure was not the material itself, but the belief that chemistry could replace craftsmanship, that sealing something away was better than understanding it, and that durability could be declared rather than earned over time. Viking shipbuilders never tried to defeat nature, because they understood something modern engineering often forgets, that nature is not an enemy to be overcome, but a system to be understood and worked with. And everything about their ships began long before a single plank was laid, deep in the forest, where trees were not chosen randomly or harvested in bulk, but selected deliberately, patiently, often years in advance. Because not every oak was suitable for the sea, shipwrights looked for slow-grown oak with straight, tight grain, trees that had grown in cold climates where short growing seasons produced dense, resilient wood. And once a tree was chosen, the most important decision was made. A decision modern builders almost completely abandoned. They did not saw the wood. They split it, because sawing cuts straight through fibers, severing the internal structure of the wood and opening pathways for water to enter, while splitting follows the natural grain, preserving the integrity of the fibers exactly as the tree grew them, creating planks that resisted moisture not through chemicals or coatings, but through their own natural structure. Wood that wanted to shed water rather than absorb it. And this single choice alone explains why Viking ships aged differently than modern wooden boats, because their planks did not behave like sponges, they behaved like living tissue. And this philosophy carried through the entire vessel. Viking ships were never designed to be rigid objects. They were designed to move, to flex, to respond to the sea, rather than resist it. Their overlapping clinker-built planks slid slightly over one another as waves passed beneath them, distributing force across the hull instead of concentrating it in one brittle point. And even the internal ribs were not bolted tightly into place. They were lashed with cordage, allowing controlled movement, controlled breathing, so that when the ship met heavy seas, the energy was absorbed and dissipated, instead of being trapped and turned into cracks, because Vikings understood that rigidity creates failure, while flexibility creates survival. And then there was pine tar. Not paint in the modern sense, but a living preservative drawn directly from the forest, produced slowly by heating pine roots and resin-rich wood in low-oxygen pits, creating a thick, dark substance that soaked deep into the planks. Instead of sealing them under a hard shell, pine tar repelled water, killed fungi, discouraged insects, and crucially still allowed moisture to escape when the sun warmed the hull, preventing internal rot. And this balance was intentional, because Vikings never tried to trap wood in a dry, artificial state. They accepted that boats live in water and that moisture will always be present. So the goal was not to eliminate it, but to manage it. And their understanding went even deeper, because some trees were treated while still alive, a practice that sounds almost mythical to modern ears. Bark was stripped from selected trees years before felling, interrupting nutrient flow and forcing the tree to flood its own heartwood with resin as a survival response, effectively pressure treating itself using its own chemistry, creating wood that was naturally rot-resistant long before it ever touched the sea. And when these planks were finally shaped, they were not forced into geometry by machines. They were guided into form by experience. Curves followed growth patterns. Joints respected fiber direction. Nothing was done blindly or at scale. Every ship was a conversation between builder, tree, and sea. And this is why Viking ships did not rely on thick hulls or brute mass for strength. They relied on systems where every part compensated for the others, where failure in one area did not mean collapse of the whole. And perhaps the most important truth their entire method accepted was that decay is inevitable. Nothing lasts forever without care. So Viking ships were never treated as finished objects. They were treated as ongoing projects, regularly hauled ashore, retarred, inspected, repaired plank by plank. Not because they were poorly made, but because they were honestly made, designed to be understood, touched, and maintained by the people who used them. And this honesty is what allowed some of them to survive centuries, because damage was visible, gradual, and manageable, unlike modern materials that hide their breakdown until it becomes catastrophic. And when you compare this approach to modern shipbuilding, the difference becomes uncomfortable, because modern boats are often designed as sealed products rather than living systems, optimized for speed of manufacture rather than lifespan, coated rather than nourished, rigid rather than adaptive, and while this makes them cheaper and faster to produce, it also makes them disposable, dependent on replacement rather than stewardship. And the deeper lesson hidden in Viking shipbuilding is not about nostalgia or romantic craftsmanship. It is about humility, about accepting that humans do not improve nature by ignoring its rules, but by listening to them. And every Viking ship that survived was not a miracle of strength, but a triumph of cooperation, a structure that worked because it respected grain instead of cutting across it, movement instead of resisting it, maintenance instead of denial. And when we look at those ships today, still holding their shape after 1,000 years, the message is not that the past was smarter in every way, but that it understood one essential truth we often forget. That durability does not come from pretending decay doesn't exist. It comes from designing systems that live with it. We abandoned this knowledge not because it stopped working, but because something faster and cheaper appeared at exactly the right historical moment, when oil was abundant, energy felt infinite, and speed became the dominant value of industrial society because fiberglass boats could be produced in hours instead of months, sprayed into molds instead of shaped by skilled hands, assembled by low-paid labor instead of master shipwrights. And as fuel remained cheap and global trade accelerated, the economics became irresistible. Skilled labor was expensive, time was expensive, patience was expensive, and traditional shipbuilding slowly vanished from trade schools, not because it failed, but because it could not compete with mass production. And hidden beneath the celebrate ion of progress was another quiet advantage that few openly discussed but many benefited from. Fiberglass boats do not last forever, not in the way wooden boats can, because a wooden boat is a system designed for renewal. Planks can be replaced, fastenings renewed, frames repaired one piece at a time, allowing the vessel to survive indefinitely as long as care and skill remain, while a fiberglass hull ages as a single chemical object, and eventually it reaches a point where repair no longer makes economic sense, where degradation is spread throughout the laminate, invisible but irreversible, and this moment creates something extremely valuable to modern industry, a replacement cycle. And replacement cycles sell more boats than repair ever could, because a boat that lasts 1,000 years is a marvel, but a boat that lasts 40 years is a business model. And this logic quietly reshaped not only marine engineering, but our entire relationship with objects, because durability was redefined from something that endures to something that performs well within a planned lifespan, after which disposal is expected. And today we are beginning to see the long-term cost of that decision, because millions of aging fiberglass hulls now sit abandoned in marinas, boatyards, fields, and shorelines across the world, creating an environmental problem that modern industry never planned to solve. Because fiberglass cannot be melted down and reused like metal, it cannot safely return to the earth like wood, and when it breaks apart it does not disappear. It fragments into microplastics, resin dust, and chemical waste that persist for centuries, slowly leaching into soil and water, turning what was once marketed as a miracle material into a long-term burden. And the irony is impossible to ignore. The Vikings built ships that demanded constant care, regular maintenance, attention, and skill, but rewarded that effort with extraordinary longevity. Vessels that could be repaired, renewed, and adapted across generations. While we built ships that promised freedom from maintenance, ease, convenience, and technological superiority, and delivered instead disposability, environmental debt, and silent decay. And this contrast reveals a deeper misunderstanding at the heart of modern design. The belief that maintenance is failure rather than responsibility, that a material which requires attention is inferior to one that hides its problems, when in reality the opposite is often true, because systems that demand care also demand awareness, inspection, and understanding, while systems that promise maintenance-free operation encourage neglect until intervention becomes impossible. And this is why the lesson of Viking shipbuilding is not to abandon modern materials entirely or romanticize the past as flawless, but to reject the idea that durability means ignoring upkeep, because true longevity does not come from sealing materials away from reality. It comes from designing systems that can be repaired, maintained, adapted, and eventually allowed to die cleanly when their useful life truly ends. And this principle applies far beyond ships. It applies to buildings, machines, infrastructure, and even social systems, because anything that cannot be repaired is ultimately disposable, no matter how advanced it appears. And when we re-examine the Viking shipwright through this lens, he no longer looks primitive or outdated. He looks like a materials engineer operating with deep empirical knowledge, someone who understood limits, trade-offs, and long-term consequences without formulas or simulations, because he knew that materials age, environments are unforgiving, and no object survives without stewardship. And every time we choose to repair instead of replace, every time we design something that can be taken apart rather than thrown away, every time we value longevity over convenience and patience over speed, we recover a fragment of that lost wisdom, not by copying the past exactly, but by remembering the mindset that made it work. The understanding that progress is not measured by how fast we can produce something, but by how long it can meaningfully exist without becoming a burden to the world it was meant to serve.